Welcome to this problem walkthrough. Today, we'll be exploring problem number 964, titled Least Operators to Express Number. This is a fascinating problem that challenges our understanding of mathematical operations and optimization techniques. Stick around as we dive into the details, break down the approaches, and explore the most efficient solutions. Let's get started. In this problem, we are tasked with expressing a given integer target using only a single digit x and the four basic arithmetic operations: addition, subtraction, multiplication, and division. The goal is to minimize the number of operators used. Importantly, the digit x can be used multiple times, and it can even be concatenated. For example, if x equals 3, the string 33 foot would represent 3 times 10 plus 3. Additionally, all intermediate and final results must remain integers, meaning no fractions or decimals are allowed at any point during the calculations. The input consists of two integers x, which is a single digit between 1 and 9, and target, which is a positive integer up to 1 billion. The output is a single integer, representing the minimum number of operators required to express the target using x. For example, consider the input where x equals 3 and the target is 19. To express 19, we can use the expression 3 multiplied by 3 multiplied by 3, then adding 3, and finally dividing by 3. This involves 3 instances of multiplication, 1 addition, and 1 division, for a total of 5 operators. Therefore, the output in this case would be 5. In another example, if x is 5 and the target is 501, we can express 501 as 5 multiplied by itself 4 times, then subtracting the product of 5 and 5, and finally adding the result of 5 divided by 5. This requires 4 multiplications, 1 subtraction, 1 addition, and 1 division, making the total number of operators 8. The output here is 8. Now, let's look at a scenario where x is 100 and the target is 100 million. In this case, we can express the target simply as 100 multiplied by itself twice. This uses only 2 multiplication operators, resulting in a total of 3 operators when we include the implicit concatenation of the digit 100. The output here is 3. These examples highlight the importance of strategically combining the operations to minimize their total count while still achieving the target. The problem also comes with a set of constraints and edge cases to consider. For example, x must be a single digit ranging from 1 to 9, and target is a positive integer up to 1 billion. Additionally, all intermediate steps must produce valid integers, so fractional values are not allowed. Edge cases include scenarios with small targets, such as target equals 1 when x is 7, which requires careful handling to minimize the operators. Another edge case is when the target is a large number, such as the maximum possible value of 1 billion, where efficiency becomes crucial. Other cases involve targets that are exact powers of x, like 729 when x is 3, or targets that are close to a power of x, such as 28 when x is 3. In these situations, the solution must balance between multiplication and addition or subtraction to find the optimal number of operators. To solve this problem effectively, we need to focus on key insights. First, since the goal is to minimize the number of operators, approaches like greedy algorithms or dynamic programming can be highly effective. These methods allow us to explore different ways of building the target, either by starting with smaller numbers and adding to them, or by breaking down larger numbers. Second, it's important to explore both directions, constructing the target upwards or deconstructing it downwards, to find the most efficient path. Finally, recursive solutions with memoization can help avoid redundant calculations, significantly improving the efficiency of the solution. By combining these strategies, we can tackle the problem systematically and handle even the largest inputs within the constraints. To start, one of the most straightforward ways to approach this problem is through a brute force method. The intuition here is to enumerate all possible expressions using the digit x and the 4 basic arithmetic operators: addition, subtraction, multiplication, and division. By recursively combining these operators in every possible way, we can check if any of the resulting expressions matches the target value. However, this approach comes with significant challenges. For example, raising x to a power, such as x to the power of k, can quickly produce large values, so we need to carefully consider the exact power being used and how the remainder fits into the expression. Additionally, because multiplication and division have higher precedence than addition and subtraction, maintaining the correct order of operations is crucial to ensure accuracy. Unfortunately, while this method is conceptually simple, it becomes computationally infeasible as the target value grows larger due to the exponential number of combinations we need to evaluate. The time complexity is exponential, and the space complexity depends on the recursion stack, making this approach impractical for solving the problem efficiently. Now, instead of blindly enumerating all possible expressions, we can take advantage of dynamic programming to optimize the solution. The key idea here is to break the problem into smaller subproblems and use memoization to avoid redundant calculations. Specifically, we can express the target as a combination of powers of x. For instance, if x equals 3 and the target is 19, we can approximate it using powers like 3 squared, which is 9, and 3 to the power of 1, which is 3. This gives us two main cases to consider: rounding down the target to the nearest lower power of x or rounding up to the next higher power of x. Each of these cases has an associated cost, as using a power like x to the power of k requires k1 multiplications. To implement this, we define a recursive function, dp, target. The base case is straightforward: if the target is 0, no operators are needed, so we return 0. For all other cases, we calculate the nearest powers of x, compute the cost for both rounding up and rounding down, and store the results in a memoization table to avoid recomputing the same values. This drastically reduces the number of calculations required compared to brute force. In terms of complexity, this dynamic programming approach is significantly more efficient. The time complexity is proportional to O log target, because we reduce the problem size by considering powers of x, which are logarithmic in nature. Similarly, the space complexity is also O log target, due to the memoization table that stores intermediate results for the subproblems. Now, why did we choose dynamic programming as our strategy? It's because this method allows us to break the problem into smaller, manageable pieces and systematically solve each one without repeating any work. By focusing on the nearest powers of x, we limit the search space and ensure that we compute the minimum number of operators required in an efficient manner. Comparing this to brute force, the trade-offs become clear. While brute force is simpler to implement, it's computationally expensive and doesn't scale well for larger targets. On the other hand, the optimized dynamic programming approach, while requiring more careful implementation, is far faster and capable of handling much larger constraints. The breakthrough insight here was recognizing that this problem could be reframed as expressing the target as a sum of terms involving powers of x, which dynamic programming is well suited to handle. Ultimately, the final decision is to use dynamic programming as it strikes the best balance between efficiency and clarity. This approach is not only scalable but also ensures that the solution remains computationally feasible for larger input sizes. By leveraging memoization and focusing on the problem's structure around powers of x, we can solve the problem in a way that is both elegant and practical. This makes dynamic programming the ideal choice for tackling this challenge. To solve this problem, we start by understanding the constraints and requirements. We are given a digit x and a target value, target, and we need to determine if the value can be expressed using exactly n instances of the digit x, combined with basic arithmetic operations like addition, subtraction, multiplication, and division, along with parentheses to control operator precedence. For example, if x is 5 and n is 3, valid expressions could be 5 plus 5 plus 5, 55-5, or even 5 by 5 plus 5. The challenge lies in systematically testing all possible combinations of operator placements and groupings to see if the target can be reached. To do this, we use a brute force approach that recursively enumerates all possible expressions. At each step, the recursive function selects subsets of the available digits, applies one of the operators, and evaluates the results for all possible groupings. This approach ensures that every valid combination is considered, though it can be computationally expensive without optimization. The algorithm hinges on breaking the problem into manageable steps. First, we define a base case for the recursion. If an expression uses exactly n instances of the digit x, we directly evaluate it. If the result matches the target, we return true, indicating success; otherwise, we return false. For the recursive case, the problem is divided into smaller subproblems. We split the remaining digits into two groups, apply one of the four operators to combine the results of these groups, and recursively evaluate all possible outcomes. To ensure correctness, we avoid invalid states, such as attempting to divide by 0, and use parentheses to handle operator precedence properly. To optimize this brute force approach, we introduce memoization. By storing the results of subproblems in a dictionary, we prevent redundant computations, as many expressions with the same subset of digits and intermediate results are likely to be evaluated multiple times. The key insights here make the recursive approach more efficient and robust. Recursive enumeration is central to the solution, as it systematically explores all possible ways to combine the digits and operators. However, pruning invalid states is equally important. By carefully handling edge cases like division by 0 and ensuring correct operator precedence, we save time and avoid unnecessary computation. Memoization is the third foundational insight. By caching intermediate results, we drastically reduce the number of redundant calculations. For example, if the same subset of digits and intermediate result is encountered again, we can simply reuse the stored result instead of recalculating it. To implement these ideas effectively, we rely on two primary data structures: a recursive function that handles the splitting of digits, the application of operators, and the evaluation of results, and a memoization dictionary that maps the current state, represented as a tuple of the number of digits used and the intermediate result, to whether it successfully leads to the target. The critical operations in this algorithm involve breaking the digits into groups, applying operators, evaluating expressions, and caching results. First, dividing the available digits into all possible subsets is essential for exploring every combination. Next, we combine the results of these subsets using one of the four arithmetic operators: addition, subtraction, multiplication, or division. To ensure correctness, we use parentheses to enforce the proper precedence of operations when evaluating expressions. Finally, we cache the results of intermediate states in a memoization dictionary to avoid redundant recomputation. This caching significantly reduces the number of recursive calls and improves efficiency. In terms of complexity, the time complexity is exponential in n, as the number of possible combinations grows rapidly with the number of digits. The space complexity is proportional to the number of unique subproblems stored in the memoization dictionary, which helps balance the computational cost at the expense of additional memory usage. This code solves the LeetCode problem least operators to express number using a dynamic programming approach with memoization. Here's the breakdown. 1. Imports an initialization asterisk. The ru_cache decorator from functools is used to cache results of recursive calls to optimize repeated computations. 2. Recursive function asterisk. The DFS target function encapsulates the dynamic programming logic. It calculates the minimum number of operations to express target using the given digit x. 3. Base cases asterisk. If target is 0, no operations are needed, so the function returns 0. If target x, the result is derived by considering whether to add or subtract x repeatedly to reach target. The minimum cost between these two approaches is returned. 4. Recursive case asterisk. For target equals x, the quotient and remainder of target divided by x are computed. Two options are considered. Option 1 asterisk. Build the number using x asterisk quotient plus remainder. Option 2 asterisk. Build the number using x asterisk quotient plus 1 x remainder. The cost of each option is computed recursively, and the smaller cost is chosen. An additional cost of 1 is added for the multiplication operation. 5. Final return asterisk. The result of the DFS target call is returned, representing the minimum number of operations needed to express target. This approach leverages memoization to avoid redundant calculations, ensuring efficient performance even for large inputs. The recursive structure elegantly handles the problem's complexity by breaking it down into smaller subproblems. Here, we start by importing the necessary libraries and defining the solution class. Inside the class, we have two key members, an integer x to store the base value, and a hashmap memo to memoize intermediate results for optimization. The main method, leastOpsExpressTarget, takes in the base x and the target number we want to express. It initializes the x and memo variables, then calls the helper method DFS to compute the minimum number of operations recursively. The DFS method is where the core logic resides. First, it handles the base cases. If the target is 0, no operations are needed, so it returns 0. If the target is less than the base x, we calculate the minimum cost of expressing the target either by adding or subtracting smaller powers of x. This ensures we account for both adding and subtracting operations when the target is smaller than the base. Next, before proceeding with further computation, we check if the target is already in the memoization map. If it is, we return the pre-computed result to avoid redundant calculations. If not, we proceed to break down the target into a quotient and remainder when divided by x. These two values represent the key components of expressing the target using powers of x. For instance, the quotient represents how many times we multiply x, while the remainder represents the leftover value we still need to express. The next step involves calculating two options: the cost of expressing the target using x multiplied by the quotient plus the remainder, and an alternative where we use x multiplied by the quotient plus 1, subtracting the excess value created by the remainder. These two options allow us to explore both adding and subtracting scenarios efficiently. To finalize the computation, we calculate the combined cost of one multiplication operation and determine the minimum between the two options. The result of this calculation is then stored in the memoization map using the target as the key. This ensures that if the same target value is encountered again, we can simply retrieve the result without recalculating it. Finally, the result is returned. This approach leverages recursion and memoization to efficiently minimize the number of operations needed to express the target using the given base x. The DFS method is the heart of this solution, enabling us to break the problem into smaller subproblems while avoiding redundant calculations through memoization. To solve this problem, we use a depth-first search approach to minimize the number of operators needed to express the target. In the first example, we are given x equals 3 and target equals 19. The initial call is DFS 19. Since 19 is greater than 3, we calculate the quotient and remainder when dividing 19 by 3. This gives us a quotient of 6 and a remainder of 1. From here, we have two options to explore. The first option is to express 19 as 3 * 6 plus 1, which leads to the recursive call DFS 6 plus 1. The second option is to express 19 as 3 * 6 plus 1, 2, which leads to DFS 7 plus 2. Now, for the first recursive call, DFS 6, we again compute the quotient and remainder when dividing 6 by 3, resulting in a quotient of 2 and a remainder of 0. This gives us two suboptions. The first is to express 6 as 3 * 2 plus 0, leading to DFS 2 plus 0, and the second is to express it as 3 * 2 plus 1, 3, leading to DFS 3 plus 3. Next, for DFS 2, since 2 is less than x, we directly compute the minimum of two possibilities, 2 * 2 1 and 2 * 3 to 2. This results in a minimum cost of 2 for DFS 2. For the second suboption of DFS 6, which is DFS 3, we reach a base case. Since the target equals x, the cost of this operation is simply 1. Combining the results, we find the minimum cost for DFS 6 by evaluating min, option 1.1, option 1.2, equals min, 2 plus 0, 1 plus 3, plus 1, which results in 3. Now, for the second main option from the initial call, we calculate DFS 7. Similar recursion occurs, and we determine that DFS 7 has a cost of 4. Finally, we compare the two main options for DFS 19 and compute min, option 1, option 2, equals min, 3 plus 1, for plus 2, plus 1. This results in a final output of 5 for the first example. In the second example, x is 5 and the target is 26. The initial call is DFS 26. Dividing 26 by 5 gives a quotient of 5 and a remainder of 1. From here, we have two options to consider. The first is to express 26 as 5 * 5 plus 1, which leads to DFS 5 plus 1. The second is to express 26 as 5 * 5 plus 1, 4, which results in DFS 6 plus 4. For the first recursive call, DFS 5, we encounter a base case, as the target equals x. Thus, the cost for DFS 5 is 1. For the second recursive call, DFS 6, recursion continues, and we calculate the result as 3. Comparing the two options, we compute min, option 1, option 2, equals min, 1 plus 1, 3 plus 4, plus 1, which results in a final output of 3 for the second example. In the third example, x is 5 and the target is 100. The initial call is DFS, 100. Dividing 100 by 5 gives a quotient of 20 and a remainder of 0. This allows two options. The first is to express 100 as 5 * 20 plus 0, leading to DFS, 20 plus 0. The second is to express 100 as 5 * 20 plus 1, 5, which results in DFS, 21 plus 5. For the first recursive call, DFS, 20, further recursion gives a result of 7. Similarly, for the second recursive call, DFS, 21, we calculate the result as 8. Finally, we compare the two options for DFS, 100, and compute min, option 1, option 2, equals min, 7 plus 0, 8 plus 5, plus 1. This gives a final output of 8 for the third example. To analyze the time complexity of our solution, we focus on the recursive function DFS and its use of memoization. The function operates in two primary cases. If the target value is smaller than the base x, the computation is straightforward and takes constant time, 1. However, when the target is greater than or equal to x, the function performs additional operations. It calculates the quotient and the remainder of the target divided by x using the divmod function, which also operates in constant time. Then, it makes recursive calls to evaluate both DFS, quotient, and DFS, quotient plus 1. The depth of these recursive calls is directly tied to the number of times the target can be divided by x, which is equivalent to the number of digits in the target when expressed in base x. This gives us a recursion depth proportional to O log_x t, where t is the maximum value of the target. Memoization plays a key role here, as it ensures that each unique state of DFS target is computed only once. The total number of unique states corresponds to the number of numbers representable in base x up to t, which is also O log_x t. This combination of recursion and memoization forms the basis of the time complexity analysis. Now, within each unique state, the operations performed are limited to a constant number of steps. These include divmod calculations, comparisons, and additions, all of which are O(1) operations. Since the total time is proportional to the number of unique states and each state takes constant time, the overall time complexity of the solution is O log_x t. Next, let's examine the space complexity. The space usage is influenced by two main factors. First, the recursive stack space is limited by the maximum recursion depth, which, as mentioned earlier, is proportional to O log_x t. Second, the memoization table stores results for each unique state, and since there are O log_x t states, the memory required for this table is also proportional to O log_x t. Each entry in the table uses constant space. Combining these two factors, the total space complexity of the solution is O log_x t. Finally, let's consider the best, average, and worst-case scenarios for this solution. In the best case, when the target is very small, such as when target x, the function resolves in constant time and space, O(1). For average cases, where the target is randomly distributed, the recursive calls are proportional to O log_x t, as determined by the depth of recursion. In the worst case, when the target is very large, the recursion depth and memoization table size both reach their maximum, resulting in a complexity of O log_x t for both time and space. Comparing this recursive, memoized approach to a brute force method highlights the efficiency gains. A brute force solution would attempt to generate and evaluate all possible expressions using the operations plus, dash, asterisk, and /, leading to exponential growth in complexity. Instead, our solution leverages base X arithmetic and dynamic programming to reduce this to a logarithmic complexity. Mathematically, this efficiency can be proven by analyzing the recursion depth, which is limited to O log_x t, and the fact that memoization ensures each unique state is computed only once, with constant time operations per state. As a result, both the time and space complexities of the solution are O log_x t. In solving this problem, there are a few common mistakes you should watch out for. First, overlooking edge cases can lead to incorrect outputs. For instance, forgetting to test scenarios where either x or target is 0 or negative might cause unexpected behavior. An example of this is when x equals 1 and target equals 2, without proper handling, your solution might loop indefinitely while trying to form the target. Next, inefficient brute force approaches can also be problematic. If you fail to prune unnecessary paths during recursion or exploration, your solution could run exponentially long. For example, if the sum in your recursive process already exceeds the target, there's no point in continuing down that path. Lastly, be cautious with floating point precision issues. Using division with floating point numbers can introduce subtle errors, especially when working with very large or very small numbers. For instance, the calculation 4/3*3 might not precisely result in 4 due to rounding errors. To avoid these pitfalls, stick to integer arithmetic wherever possible. Another common mistake revolves around ignoring operator precedence. Misinterpreting how expressions are evaluated can lead to incorrect results. For example, in the expression 2 plus 3*4, the multiplication should take precedence, resulting in 14 instead of 20. To avoid errors, explicitly use parentheses or follow standard precedence rules. Additionally, not accounting for repeated digits can cause incomplete solutions. Some problems allow forming numbers like 22 by concatenating 2's, and overlooking this can lead to incorrect answers. Make sure your approach can handle scenarios where digits are repeated or concatenated to form larger numbers when needed. When approaching this problem in an interview setting, there are several insights that can make your solution stand out. First, pattern recognition is key. Many problems involving arithmetic operators, like this one, benefit from recursion combined with memoization. This helps reduce redundant computations and improves efficiency. Optimal pruning is another important point to discuss. For example, if x equals 5, you can avoid exploring paths where the sum already exceeds the target by cutting off those branches early. Thinking iteratively is also valuable. While recursion is common, iterative dynamic programming can sometimes be easier to debug and optimize. Another helpful strategy is modular thinking, breaking the solution into steps, such as generating expressions first and evaluating them second. This separation simplifies debugging and makes your code more manageable. Finally, strong communication is crucial. Be prepared to clearly explain how your solution handles edge cases and avoids pitfalls like infinite loops or invalid computations. To strengthen your understanding of this problem, it's useful to explore related problems that share similar concepts. For example, LeetCode 282, titled Expression Add Operators, involves inserting arithmetic operators to form a target value, making it conceptually similar. Another related problem is LeetCode 227, Basic Calculator 2, which focuses on evaluating arithmetic expressions while accounting for operator precedence. LeetCode 772, Basic Calculator 3, builds on that by including parentheses for grouping operations, which adds another layer of complexity. Lastly, LeetCode 306, Additive Number, involves forming numbers by adding sequences, which also requires careful handling of numbers and operations. Studying these problems can provide additional insights and strategies that are applicable to this challenge. There are several alternative approaches you can consider when solving this problem, each with its own trade-offs. One option is recursive backtracking, where you enumerate all possible expressions using recursion and add early termination conditions to prune invalid paths. This method is simple to implement but can be slow for large inputs. Another approach is dynamic programming, or DP, where you use a DP table to store intermediate results. For example, DP I could represent all possible results using the first I digits. While this approach is typically faster for large inputs, it's more complex to implement. Lastly, iterative BFS or DFS can also be used to generate expressions level by level or depth by depth. While these approaches avoid stack overflow issues inherent in recursion, they can be more memory intensive. Each of these methods has its strengths and weaknesses, so choose the one that best fits the problem constraints and input size. Great job reaching the end of this problem walkthrough. To summarize, we tackled problem number 964, discussed multiple approaches, and highlighted the importance of optimization techniques like dynamic programming. Remember, practice makes perfect, so keep solving similar problems to build your skills. Thank you for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!